use not shares with share 对，然后这个 OK
哦，对对是是，这个从来没用过，是的。
这个是可以投币的，如果你要加热，然后这个是
用哦，对对对，
嗯
烧起来，
这个是今天那个没有现在光有长路是这样的，可以就是
好，
这个
也是超过100，
过100啊，对这个这样。在哪找你打开始这个稍微好了。
Okay, I need a sci-fi also. Yeah. Is QM sci-fi is okay. Okay, sure. So you purchase your system. Okay, cool.
全部啊，Station Plasmas 在洗上，但已经有胶的地方有，那底下有胶的，这样能洗吧？
可以洗，
而且胶整个
洗来会掉，洗来会掉了，但是那重新粘，对的，是的。
他就拿了屁股，然后我上次买个新的过来，然后给他屁股洗了，这里边。
So we will use the again we will use the PDMS as a demonstration, and we will do both spectroscopy and the mapping, and it is highly preferred to use the spherical probes because the radius will be fixed. So the AC change will be just due to the radius change. You don't need to worry about the radius of your probe is changing. So it's highly preferred. And for the probes, Bruker provides two options. One is add with -30. It means the radius of the end sphere is about 30 nanometers. And another one is -125. And of course, this one with -125, it will be larger, so the resolution will be lower, but it provides a higher stability for the modulation of the spectroscopy. So if you're doing the spectroscopy, we recommend the -125, and for imaging, you can use the -30. Yeah, of course you can use other, you can use probes from other companies. It's okay. It's just the same thing. The industry follow the same procedures, and Bruker provide the QR code to scan it. So, and we go to the setup. And then we can click on the scan QR code and just put the QR code, and it can read the spring constant, the resonance frequency, and the quality factor, and the tip radius, and the half angle out. So you just click it, and it will record everything. Of course, if you purchase probes from other companies, they have the same stuff. Yeah. So since it's new probe, so we will just use the first one. Okay, so they will wait better to choose the correct numbers. and we don't want to mess them because it will mess the calibration numbers. So if we just take one and we will just choose this one. So I click on this one and use this record. So it came out like this.
Yeah, always.
Uh,
we need to adjust it.
Okay. Let's get it done now. Yeah, Allen key, yes. I think this one is. Okay, let's focus on the probes. And then we can go to our samples. And we will do sci-fi first because we need to calibrate this. Oh?
We start the software.
No.
100.
No.
我建156了，小心。
对对，应该是不会的。哎，我们又点出来。 已经 disable 掉了。还是调一根这个线来吧，调根线来，后面让 Ivory 他们来换好了，调一根这个线来好。
少之前
不是，我觉得这是应该是接口有点问题。
做了，做温度了。
啊，可以先不做温度，先不做温度，但它这个显示是个错的，但是它没有加热。对，先做室温的。So we will do a calibration on the sci-fi first. Okay, and I prefer go to the setups and do the advanced calibration. Okay, and click on the advanced. And I don't even need to do the thermal tune because it's done to get the spring constant. I can direct go engage. Okay, and then we just do a force curves 300 nanometer 0.2 is okay, and click the ramp. Since it's a large sphere, so it will sense a large the adhesion force is okay. So it told us unable to validate the new deflection sensitivity because there's no original sensitivity because we don't do thermal tune, so it's okay. Just type in, and we don't need it to update the spring constant because our spring constant is done by the broker. So I uncheck this one and update the value. And of course, you can change the fate range a little bit, but it's okay. For example, you can just the to drag the one to on the extend part, and then I click update and values and update values. Then the difference sensitivity and swing constant are done, and I can do the peak stepping as well. And of course, we don't need the peak stepping to do image for us. We just need the peak stepping to do a rough scanning first, and then we use peak stepping to find our interested area. So I just done this step. Okay, that's it. Then I can return and save updated values. I don't need to calibrate the other step because it's already done. Because I don't need the other frequencies. I just use one for imaging. And then it's done. I click on OK, and today I prefer not to take out the sci-fi samples because we need the sci-fi samples to do more calibration for us, because this is a dynamic analysis. We need to know the frequencies, and we need to capture the Z. We need to capture the vertical values, and then the phase difference of them is the loss tangent. But the idea is, even our instrument is perfect, there will be some phase difference between the Z and the vertical itself due to the piezo. So we need to use sci-fi to calibrate what's the intrinsic difference of phase of the vertical and the piezo. Because the sci-fi we suppose is pure elastic. The phase difference on the sci-fi should be 0. So if we say some phase difference, that will be due to the instrument itself. So this step is to calibrate the phase difference. But and now I do not know my samples anymore. I do not even know anything about my samples. So I would do sample first, and then go back to calibrate the phase difference using sci-fi. So we will just do sample at first, and then I would choose the PDMS soft, and I put it somewhere here. Okay, and then I can do imaging. Okay, that's the surface. Yeah. Okay, then I decide to no. Maybe I can adjust it. Okay, then I can engage on these samples. So for the this is our the so-called the mirror view mirror view function, and the mirror view, it gives us a canvas, and on the canvas we can define what we want to do, and we can use screw. We can use the scroll to zoom or zoom out on this canvas, and on the canvas there is this kind of blue dash, and or we can click on this zoom to scan range. This one shows the total area the scanner can scan, the scanner can move, which is about 90 micrometers times 90 micrometers. So we can do AFM scanning inside this range, So I can click on this, goes to the scan, goes to the total scan range. So the next, what I will do, I will engage. Once engaged, the probe will be in the center, and then I can draw any shape I want, and to do the AFM imaging. So I engage first. Okay, I still found the wrong surface. It's two. So another layer to go up. Oh yeah, that's the surface. Oh, here. Okay, it's a quite soft material. Okay, so once it's stabilized, this one will show green. That means the system is ready. You can draw any shapes you want on the surface. And we have three options. The one is to do a AFM scanning. So that's do imaging. Second is we can do a force volume, do force go on each point we define. And the third is we define a position and then do force curve. So that's the three one we can do. So usually I will starting with the AFM scanning to do a peak force QM image on a certain area. So I can choose this one, and my mouse will change to this cross, and I can draw a shape. And then I can click on this pan tool to move my total the canvas, or I can click on the mouse to move the scan area. So I can just change the move scan areas inside this scanning range, this dash. And of course, I change this one is I changing the X offset and the Y offset. It's the same things, or you can just change here. The position will change, but the mirror will just make this is a graphic user interface. So I can also surround the I'm sorry, I can rotate my scans to be random shapes. I can zoom or zoom out. It's okay. So basically, let's do 10 micrometers, and maybe I will do it in the center, and I want to do zero rotation. And then we can click on this zoom to selected, and then the area, the image show here will be our scanning area, or we can go to a zoom to scan range to goes back to the total lighting. Okay, and then I need to adjust my parameters. So look at this force curves. So it looks like my peak force amplitude may be too small because it's already nearly the end of the adhesions. So I changed it, I increased it to 200 nanometers. And then 400 piconewton may be okay, maybe not. I don't know. So let's just give it a try. And this one will be the tip, will be the mirror image. We can also change back to the classic AFM 4 channels view is okay. And then we click on the start scanning and then it will start. Before that, usually we will define our capture window. Oh, sorry, capture folder. So I click on this capture folder. So
E drive, E drive,
E drive
like
training. Okay, and then yeah, and this is nDMA training, and I'm using the PDMS soft sample. Okay, so this is a QM image. So I'm good to go. So I click on this start scanning. So it will start to scan the selected area. And I'm sorry, it is kind of slow. So it took a while to start the scanning. So it's just the same as an AFM scanning. We need to adjust the force. We need to adjust the gain. So if you're familiar with the gain looks okay, but if you want to make it better, you can increase the gain to reduce the error to as small as you preferred. Okay, that's maybe too much. I will reduce it a little bit. Then that's about a good error images. And our deformation can be observed on the deformation channel to say what it looks like. So the deformation channel looks unstable because the force may be too small, too much. So let's play around with the force. So I increase the force to see if I can make it more stable. Because my force is too small, so they cannot capture the deformation very accurately. So I decided to increase my force slightly. And I need to reduce the gain a little bit to make it stable. Okay, so that's about kind of stable now. So yeah, that's kind of stable now. So yeah, it's I say the gain, I say everything. You can tell the spring constant, the tip radius, blah blah. They are all done. So once you say this kind of shape, you say this kind of shape, there is a big loop between the trace and the retrace. It means I indent my sample significantly. From left to right, it has a large deformation. So you will observe this kind of loop, the trace and the retrace. This looks similar, but it's not superposition with each other because I apply too large force. So this will be such kind of damp. But if your force is too small, the morphology will be good. Say, once you reduce the force, the morphology will be better. But you lose the deformation because the deformation is so small, they cannot calculate it very correctly. So yeah, that's the way of how we do it. If we want good images, we may want to use the small force. If we want to capture the mechanicals more stable, we may need to apply larger force. Yeah. Okay, so this one doesn't matter because we do not use the pivot QM to do image for us. We just need to define an area, and then inside the area we want to do our nanoDMA mapping or a spectroscopy. Okay, then I maybe choose my morphology and I don't need to finish. So I can click on the stop scanning and then I can choose the points to do force curves and then use force curves to define my nanoDMA. For example, I choose the add a ramp scan only and then do maybe here. I want to do a force curve here. The purpose now is I need to define what's the maximum force I want to apply, what's the ramp size, how long I want to retract my probe. I say a large adhesion force, so it's better to apply a large ramp size. I don't need it to be fast, so I just change it to 1 Hertz. And the force, I don't know, maybe 1000. I don't need any hold now. I don't need any hold now because I just need to define the force I want to apply. So change it to 0. And then I do a single curve. And it will be shown in the ramp view. Okay, it gave me a curve. Let's say it's really large adhesion force, so they did not even capture the force correctly. So I increase maybe to 2 nanonewton. And then once you change the parameters, they will automatically change the position for you. So it's okay. So I can maybe change to another area and then click on do it. Okay, still again, I did not capture the my force because it's sense too large attraction force or adhesion force. So I need to play more harder. So I add another one maybe here. Sorry, click on this, and add it here. Okay, I would try 5 nanonewton this time. Okay, again, still not capture my force. Is the large attraction force. Maybe I need to do a continuous ramp. And increase my force. Okay, now it's back. Now it's back. Now I can stably capture force and maybe do it relatively slow. And to reduce maybe 5, to say if I can capture some stable force curve. Okay, now it's kind of stable. I would take a look on my force curves so we can click on the folder we are saving our data. And usually if you do not click the capture, their data will be saved in the auto capture folder. If you click on it, then it's okay. It will save the on your in your defined folder. So let's take a look at my force curves. Oh no, that's not the one. Oh, that's not the one. Let me stop and capture last. Okay, that's the one. Okay, the purpose now is I need to know the deformation under the 5 nanonewton. So I do all the basic things. Okay, and then I take a look on the deformation. So the deformation now is about 25 or 30 nanonewtons under 5 nanonewton. So the sphere of my probes is about 125. So I indent now about 20 nanonewton, maybe too much. So I would reduce it to maybe 3 nanonewton. Okay, it told me it's linked to somewhere, so I would jump and do another one next to it. And I would try 3 nanonewton and do a force curve on it. Okay, it's good. So I capture one. The same game, I do the baseline correction. And I do now it's about, yeah, it's about 15 or something. It's okay. So I finally decide my force to be 3 nanonewton or something like that. And then I can do my next is I would generate the script I want. I would generate a script I want. So I want to do maybe from 0.1 hertz to 100 hertz, but I want to avoid the AC frequencies. So I set up my maximum to be 95. But it's okay. You can use 100, not too much. And then under the advanced, I need to set my reference frequencies. And my reference frequencies is 90. And then you can say the reference series. The red ones are all the reference frequencies, and the blue one is the frequencies it generated for us. So it will definitely generate the lowest frequency and the highest frequency you set, and the others is generated randomly. Randomly. And if you don't like this set, you can refresh. Yeah, it's generated randomly, same as the bulk DMA. And the frequencies, typically we prefer shuffle and shuffling. So it will be a dual large, small, large, small, large, small, large, small. We don't they prefer not to do a series like we do it decreasing or increasing, because in the theory of the DMA, they found that the polymers is kind of like they can remember their properties. So if you increase the frequencies or decrease frequencies, they will kind of remember the previous step, because you are unchained, you're opening the polymer chains. So they prefer to do the shuffling. They don't want the polymers to remember their previous status. So high note, high note, high note, we prefer the shuffle. Okay, and then the force we applied, that's my game play around. So I decided to use 3 nanonewtons. So I type in 3 nanonewtons here, and then it can define the modulation step. It will be 600. And then inside the advanced, I need to define the size, blah, blah, blah stuff. So I tried 1 micrometer, it's good. So I would use 100 1 micrometer, 1000 nanometers. The velocity is just for up, down speed. So it doesn't matter. So you can use 500, or if you want to make it gentle, use 300, it's okay. And then for the relaxation segment, that's the point here, is we want our sample to creep for a while. So usually it will be 30 or 50 seconds is okay. So normally people use 30 micrometer, 30 seconds. And the next two numbers is by default. It is used to define how many cycles we want to do. For example, for 0.1 hertz, the period is 10 seconds. So if you just do a one sine wave, it's 10 seconds. But one sine wave may not be enough to capture its amplitude. So usually we need to do several periods, enough data to calculate the amplitude, and then we can do our mathematics. So this minimum cycles per segment is to define how many periods you want to do for one frequencies. So the larger this one, it will take a longer time, especially for those low frequencies. So we can consider this segment, the whole experience will take the time, the time consumed is by this 0.1 hertz. So we need to do here. So for example, you can say the total time will be 7 minutes. If I reduce this segment to 10, I will reduce the time for the 0.1 hertz. It will drop back to, yeah, it will change significantly for the low frequencies. So up to you. The larger this number, the longer time it consumed, but your data will be more stable. And for each cycle, we need to connect the numbers. So that's our sampling rate. So that means for one period of sine wave, how many data points you want to capture. So this one doesn't matter. No matter how you increase or decrease this one, it will not change the time, because the period is defined by the frequency, and the numbers of periods you want to capture is divided by this minimum cycles per segment. So this one does not change. It's 100 or 50 does not change the numbers you take. Of course, you want to make your samples, your data to be stable. You can increase this one to increase the sampling rate. Normally 50 is enough. And the next is about the minimum segment of time. That's for the high frequency. For example, for 100 hertz, the period is just 10 milliseconds. I'm sorry. No. Yeah. 10 milliseconds. 10 milliseconds. And if you just do 10, I'm sorry. For example, if you are using the high frequency, if you are doing 1 kilohertz, one period is just 1 millisecond. And 1 millisecond is just, even if you do 10 cycles, it is just 10 milliseconds. And for those, we may not have enough data. So we would define a minimum segment time. So for those high frequency stuff, they have to continue for this 0.1 seconds, even they have done over 10 cycles. So this is for the lowest one, this is for the highest frequencies. And then the others we don't need to worry about. So after that, we defined our segments. And sometimes you can just write down the loads for yourself to know what the parameters you set. For example, I would say I use 0.1 to 95 hertz, and the force I apply is 3 nanonewton, and you can write down the modulation, or if you just use it automatically, it will be 1/5. And I use the 1000 nanometer size, and I hold my samples for 30 seconds clip, and just write some notes for myself, and then I would save my script. And for example, I can save my script inside the folder. It's the DMA for PDMS. Okay, I save it, so it will be somewhere here, and then I can close this window. Then my job is I will do these force curves on a defined point. For example, I want to do 5 of them. I'm sorry, let's just do 2. Just do 2. So that it will generate 2 points. So you can right click to create run points. So it will generate 2 points. And then let's go to the ramp view. Oh no. Oh, one needs a window something. There should be a window somewhere. Sorry. Maybe something wrong. Sorry, let's go back to the image. And then go back to force curve. Something wrong. I cannot add my script here. I cannot introduce my script here. Run through. Script generator. Sorry, I need to figure out on something on the software. There's a window somewhere. Oh yeah, it's here. Item property. It's here. I fix it somewhere. Minimize. Okay. Oh, yeah. Now it's good. Okay. Now it's good. Okay. So I choose my. So I think I just let's do 1 point. Let's just choose the point here. So it shows green, and then on this window, I click on the use script, click yes, and then I select the script, and then I found the script I have, which is in the E drive and the R training, the PDMS. Okay, then it will combine PDMS script with it. Then we can click. Of course, you can click capture first, or if not, you will find it in the auto capture folder. So you can click capture, click start. Then it starts. So first goes down. Okay, reach my force, and then continue to hold for 30 seconds. Okay, it start to modulate. It was starting with the reference frequency at the beginning, and then you can say now they are doing some on this low frequencies. Now I think this one is the 0.1. It's super slow.
那个扫描通道里面那个 height sensor 和
嗯
height 它的区别是什么？
height 是皮轴的运动，就是我加电压让皮轴去动。height sensor 是压电陶瓷上的皮轴上面的一个传感器读出来的它的实时的位置。
height sensor 其实就是样品的一个高度。
其实它们两个都是样品的高度，只是一个是更准一点而已。就是你可以认为，height 是你想往前走50米，然后你真的走了多少米是你靠尺或者靠眼睛量出来的。
对
对，然后所以height sensor我们更觉得它会更准一点。Okay, just last 30 seconds. Okay, it will retract. And then this one is done. But it's not enough for our data. So let's open it and I will withdraw here. And we need to finish the whole cycle unless we add the phase difference between the height sensor and the vertical. So I need to go to my sci-fi. If you do it if you do it frequently, you can just remember the position. Okay, I will increase here on the sci-fi. Okay, I found some clean areas, and I will do a single. I will do also do a ramp on the clean area. And the point is, we should not change any parameters, but use the same script we used for your samples. And then I click go, let it down. Oh, maybe change it to sci-fi.
它有那种按钮可以把这个图片变成 CCD 的CCD 上的那种照片吗？
有，在 Mirror View 这里，您点这个，它就变成 CAD 上的照片了。So for sci-fi calibration, use the same script. Do not change any parameter. Just use the same script. Two minutes. Just scripting is to some time.
所以样品和这个安保是用同一个温度的，如果比方说
Yeah. Okay, done. And then we have this sci-fi curves. So we open the PDMS curves. And then under the PDMS curve, we click on this AFM, let me say, yeah. We click on the AFM DMA single script. So open the PDMS one, and then we click on the import calibration. And then we put the sci-fi. Oh, no, I'm sorry. we need to open the sci-fi. We need to open the sci-fi and click on the single script, and we do run calibration. And then that's the sci-fi one. We add it to ret, click on OK, and let it do. So it will calculate the phase angle, the phase difference on each segment. And then we click on the export calibration. But it should be automatically exported, but just to double check it is correctly exported. And then go to the sample, PDMS or other samples, click on the import calibration. And this the calibration results. And then the modulus is done. So we have the E prime, and we can set we can click on this E double prime as the set as the y-axis, and for example we can even set the E the tangent delta. What is tangent delta? Yeah, E prime over E tangent delta. So that's about the results. So usually the E prime, the storage modulus should be linear. E double prime, it will be smaller. Usually the E double prime will be smaller. And it's something like this. And on the right side, you should be able to say 5 data points, something like this. That's the reference frequencies. Yeah, the reference frequency several times and put it here. And yeah. In principle, the 5-1 should be completely the same, but the brokers, after their algorithms, they will calculate back the modulus using the radius they calculate. So it shows slightly different, but yeah, that's the one. And we can say, click on the reference, they generate this contact radius, this AC against time. That's the curve. So with that, the result is done. Yeah. So in the afternoon, we will do the mapping. Okay. And then we can withdraw. Yeah. Okay, let's continue and finish the imaging parts. And the imaging in nanoDMA is it's the same as the force volume. So again, we also need to do calibration on the sci-fi. So and we don't know the parameters, so we need to figure the parameters out on sample, and then we came back to sci-fi for calibration. Oh, oh, oh. Huh? Touch something. Okay. we find a certain area and then we engage on the surface. Now it's stable. Yeah, now it's stable. Yeah, so just the connector here. So this one is sample heater. Sample heater cable. Okay, and then we can just do now we need to do the last one. That's the force volume scan. So we just click the force volume scan and choose a certain area. For example, I make it 20 micrometer. And I wanted to be maybe 32 times 32. And I need to define the ramp size, the force curves, and I can use the same one as the 3 newton. The only thing I need to do, we need to add the hold time. Hold time for the force volume, we can only add one frequency. So for the modulation, so usually 100 milliseconds is enough. Yeah, and then I can define the J. I need to do the modulation. So I apply the 1 millivolts, maybe good, maybe not, but we need to try. And the frequency, we tried the 100 hertz to avoid the AC. So I use 90 hertz. I use 90 hertz. And then I can click on the force one channel and then click start. Yeah, then it starts. Then it starts. And we can take a look, we can change it to the hold segments. So it will just show the forces, the modulation during the hold. Oh, sorry, we need to increase the ramp rate to increase the speed. So 10 hertz or 20 hertz should be also okay. Okay, let me take a look at the height sensor. Look on the hold. Yeah. Yeah, we can see the kind of the wave. probe may be too soft for this one.
How do you judge the
Currently, no, I need to wait until the done. Yeah. So it's actually almost it's similar stuff. It's way let me check the time. Yeah. Similarly, we will also need to check the amplitude of the force to say if it match our the criteria that we don't want the deformation to be too large. So for the 3 nanonewton, we guess the modulation should be around the modulation should be around the tens or 15 nanometers deformation. And after the modulation, we want the amplitude of the modulation to be around maybe 3 or 4 nanometers. The 1/5. Maybe something. How to say drive? I say not so noise on the force. And maybe this 1 millivolts is not enough. So from this we can say the wave. Let's capture now to say results. Force. This X, I take a look at the hold. No, hold segment. Maybe too small. Maybe too small. The deflection. It's hard to say. Hard to say the modulation. With this one. No. The data, how to capture, refresh. Oops, why the data? Not here. Yeah, it's not good. It's because I cannot say clearly the force. This way, let me try high sensor. Yeah, I did not say dragging out. No, force curve is not good. Let me just do a normal force curve. Because I did not say this dragging out part. Yeah, this one is normal. Yeah, this one is normal. At last. And we can take a look, can click on the hold analysis, take a look on the hold, okay? So it's okay. Where's this noise came from? Okay, usually I would transfer it into the nanometer scales to check about the amplitude of the fall of the deflection, and it should be let me click on the modulation analysis, and I should be able to say those kind of the amplitude, to say those kind of amplitude, and the amplitude now it's just 0.6 nanometer. That's too small. That's too small. So I think I need to increase the modulation amplitude to make it to reach maybe 2 or 3 nanometers, something like that. So I click another one and make it maybe 5. Okay, now I can see a clearly wave, and then I still click on the modulation analysis, and it can firstly it can substrate the creep, and then it can generate it will fit the sine wave and to give out the amplitude value, and I want it to be the matrix. As such, I need to know the amplitude. So the amplitude is about 2 nanometers. So my deformation is about 15. And so maybe I can just write it down. So I'm doing something like this, and my original deformation is about 15, and I want this a modulation to be less than 1/5 of my deformation. So this one I need to want to be 3 or 2 nanometers, and then I captured around 3 nanometers. That's good enough. So so I have 3 nanometer deformation. I have 3 nanometers deflection, and the total Z. Let's check the Z, and about height sensor. Click on the modulation analysis. It will give the height sensor amplitude. The height sensor amplitude is about 3 nanometers. So the deformation is just 0.4. 0.4 is still quite small. It's still quite small. So maybe you can give it a more 8. Okay. So we take a look at the height sensor first. And height sensor now it's about use the matrix. It's about 5 or 6 nanometers, and the deflection. I use the matrix. The deflection is about 4 nanometers, so it gives about 1 or 2. You can continue increase by it's something like that. Okay, and then we can do the imaging. On each point, we do the imaging. Okay, and I can use this one in the table. Yeah, the software itself, you can just choose, yeah, it's the false volume stuff. And once it's done, we can open it in the nanoDMA stuff and import the calibration results, then it's done. 你们那台也有这个对吧？我记得你们那台也有这个对吧？
有，
嗯，
可以用。
你们做高分子其实还是用得到这个东西的。
就之前培训的时候，就是培训过，但是我们也做过2次。
嗯，
但是就不知道它那个数据准不准。
OK，没问题，数据它是准的，没问题，这个
其实之前我们做那个 QM 的时候，DS 都没教的。
那还是得叫。你做QM 不叫无所谓，但这个玩意它就是得叫的，因为这个东西它纯靠 DS 是它的第一步关键，它 DS 不叫，后面东西都不对。Yes。
像我们那个样的话，场一下也能做是吧？
可以说，
这个话就把这个数据给它补。
嗯。行，的。哎，so once it's done, we still need to work on the sci-fi again. So the same parameters and do it on sci-fi. 都可以，哪里都可以。只是我没有开真空，所以我就放它左边，它是可以吸的。我们要放中间，因为要开真空吸附，所以就放中间。他们这个左边有一个专门的多的样品台，就可以这个吸在左边。必须要固定，对，无论真空还是磁吸都得固定。它没有真空，只有中间有真空。
磁性的可以。
磁性在哪里都可以，磁性你用这个可以在哪里都行。啊，力太小了吗？Maybe 可以这边，yeah, force is too small. And when you do sci-fi, you don't need to do large scan size. You don't need to generate too much points. So usually on sci-fi, I would just do maybe 1 micrometer by 1 micrometer, and 4 by 4 that's enough. Yeah. Okay. And then I can click on the force volume, and maybe that's a choose 2 micrometer. And I just change this to 4. And those others do not change. Those do not change. And then we can good to go. Oh, same sci-fi. Okay, and then we can open the data PDMS your samples results. Oh no, not this one. Yeah, it's this one. It's this one. No. Mm. Why the force is like this? Okay, anyway, and then we click on the AFL NDMA, and there will be a calibrate. It's on, and click on calibrate, and choose the sci-fi. I think the sci-fi is this one. Am I opening the wrong number? Yeah. Open the one. DMA should be in the auto capture, and NDMA. This one should be my. Oh yeah, that's the one. That's the one. That's the one. And click on AF NDMA, calibrate, and open the sci-fi. And then it's done. And then it's done. And from here, you can choose the North modulus, storage modulus, or North tangent, or North tangent. Yeah, yeah. That shows the distribution. Yeah, yeah. It's right here in easy here. Okay. And once it's done, we click withdraw. That's it. Yeah. Okay. I think that's all. That's all. That's complete done.
Yeah, thank you, thank you.
没事。The cable I will get move and send to you.
这那个温度跟你放的是完全没有
没有
差的，
没有
这
没有。
我自己一些那个有看到。
没有用温度，没有。呀，我这个蓝宝石放上面是啊。
所以平常做了，他一边放蓝宝石，一边说的蓝宝石咖啡就可以了。
他们就是中南气，你看
也是蓝宝石的，直接那条件就直接就比如每次。
不用，他们这个东西就北水往里充气，他们碳真夹上都是有造型。你看看你们是不是有这一套东西？如果有就不用买。
如果有这个就得买。
不，有这套碳真夹应该也带了。
哦，你说的意思不是说带的这种。
不用，它本身是你看它这是充气的。
样品站在蓝宝石的话，是只用普通上面照这样的，应该什么特殊的？
一般他们这种样品都是 sectioning 做的，
但是
冷冻泡切，因为你们可能有这种设备吧？
没有，
有冷冻泡应该是切片机，别人应该是有切片机的。
哦，切片机，
对，冷冻切片的，对，冷冻切片的。然后那个切片切的很薄一片，然后直接就给铺在上面。它会吸附上去的，对。哪个流程？有的加热冷却的那个我们我们也是有的。其实只要你们有这个设置，然后外面氮气吸管一接，它就直接进去了。就看你们有没有这套设备的，这个就类似这样的，对，就类似这样管子器。
这单期是什么时候选？是看你样品的
因为理论上我们建议是你超过100度就最好空气，
怕氧化，
就怕氧化，把它沟通到这个熏到反动板。对，然后我赶紧走了。然后这个吸管在这接好的那个白色的管子，它应该是。记得我接好就是这样子。
那个
水是直接接到这里来的，没问题的。然后白色管是没接的，白色管就是用来接气的。游泳老师之前。
说水也就是这里。
对，水也就这里面的水。
哦，那就是说换一下也没有这一套的。
对，是。
你让刘洋走了，我再帮你切一下。哎，因为刘洋着急。
好。
所以你先走。
好。
给他切一下。那都是你拿的吧？
行。回去再。
回去再。你确定这东西能上飞机不？如果不能，我就放在我的包里。反正我就给你把这个弄出来了。你这个因为很硬，你得上很硬的样子，看真的。干啥呀？
是镀的是那个银2级，但是不一定是那个程度，因为是拿那个原料粉卸上去，那个磁贴射上去。
啊，我就不校准那个探针了，我就给你个纸啊。咱们先看看，咱们找个525的探针。我一会儿让那个谁拿过来，你这个可能要先上个300吧，压不动就是上525。
是换探针就得看校准。
那肯定啊，你每次装开不同的探针。
现在是
这个探针他们已经拿下来了，他这个探针是刚才给你们做那个
校准。
这不是在做校准，刚才是在做 nanoDMA。那个 nanoDMA 的这个探针是后面这个 R 是已经校准过了的，K 也校准过了，所以它只校了一个顶端跟3次。然后呢，刚才的演示是在做啥？你们听明白了刚才的演示在做啥了吗？显然没听明白是吧？很显然没听。你给我一个那个300或者525的针。
哦，
40个 G 盘
40个 G 盘，那525吧，525都不一定能压得住啊。
是元器不要那个。
啊，不是，就普通个525就可以了。你这个应该是压不动，因为咱们那不是说了嘛，到20 G 盘你就得上康泰的有公司了。我那次昨天不是给你们发了吗？刚才的演示显然你一个都没听懂。刚才演示在做啥？
我就听到
大概懂了。
你看这些，
这个是300，但500我们没有我们全都是校准过的。
OK， 这个哈，那就用这个吧哈，可能压不动哈。但它是这样，刚才的意思是说，我的这个材料是粘弹性材料的时候，它的这个硬度是随着你的这个速度，是你在里面的搅动的速度是变化的，就是阳式模量是随着时间而变的。咱们现在咱们做的 QM 里面的这个模量是一个定值，不随着时间而变化。刚才是在做怎么随着时间而变化的。那么随着时间而变化，你不能说我放在这里一直放着看它的硬度多少，对吧？所以呢，我们就把它转到那个频率上面去，就是高频这个东西就硬，就跟这个水一样，对吧？我在里面搅得快的话，你自己都觉得这水是硬的，对不对？啊，然后那你那个速度慢的时候呢，它是软的，所以我在看它这个硬度随着时间而变。对啊，那像咱们现在做的这种材料，那就不是这种材料，它的阳式模量是一个定值啊，它不随着时间而变化。这怎么这种概念得先要理解啊，概念得要先理解。那个，或者你来帮我装吧，我没有意见。
没事。
那个皮肤的玻璃为啥那个3238？
因为它慢，咱为了增快速度。
可以很高的领，做半天。
对呀，你想做128乘128可以啊，你没看到时间长吗？对吧？因为你这个东西是咱们在这个 QM 里面你去看的时候 ，P 个 QM 里面你去看的时候，你做256乘256，大概是4分钟就可以做到，对吧？但是这种呢，是因为我这么上来下去，我的速度慢，然后又尤其像咱们刚才做的实验，我下去以后我又停在那里，对吧？你加上这个时间再起来，再到第二个点下来，再停下来，时间不长嘛。那咱要做128乘128，咱可能做好几个小时，那没有时间了。
那其实它一张图的话，32乘32的话，就32平方个点那个。
一共多少个点？就是说，在你扫描这个区域里面，你先给了个扫描区域，对吧？这个区域比方说是5个微米乘5个微米的，那32就是这一排是32个点，加32个行，但 totally 就是32平方。
哎，老师你带一下。
啊，不用带，不用带，
没有
这么几
没有，
个
我录下来，我以后我就是给人看觉得。
OK，
对
因为它这个样品很硬，我估计是压不动的啊，我估计咱们这个探针是压不动的。它40个基帕的材料，
还有对
就是525可能只能试一试，你再到了超过20个基帕，这种方法就不适合了。你要上那种接触共振的那种方法，就是探针和样品组成一个系统，然后又去震它，让震样品，那这种方法是做不了了的，因为你没有压入量了，你没有压入量了，你现在可以先试一个，就是我们把那个参数放上去，先压一个滤曲线，先去看看它的那个压入量是多少。如果压不动，那就你的模量是出来的。
因为我之前其实有个师弟说他也测过，就是
你这上一个金刚石的
不是
40的可能还行，
但是他也是测一个可能模量差不多47号，然后测完之后还和那个纳米压和那个结果比较，好像还对的差不多，就是
你调参数你有时候也能调出来，但是对不对就不知道了，因为这种方法本身你就是不适合了，就是太大了咱们压不动，你要不然你就上金刚石的那根探针试一试。
金刚石的，是
那个金刚石的那个探针 K 是350的，你查那个 K 值，查那个 K 值，
就是说有可能他是用金刚石来侦测的。
金刚石的实际上是也有到那个时候也已经有很大误差了。如果我的这个压入深，就是我的这个样品的形变拿不到2个纳米以上，你测出来的几乎就是不正确。所以上了 G 帕级的这种材料，这种几十个 G 帕级的这种材料，咱们基本上不用这种方法，就是上接触共振。
这老师是这个仪器吗？
是是这个仪器，然后有一个振荡器，他们没有买有个振荡器，然后震那个样品，让那个样品震起来。然后这个东西，那个一震的时候，我这个探针和样品形成了一个系统。我震的时候，我就可以找到它的那个共振体它的这个 different material 那个 reference 那个系统的 contact frequency 是不一样的。我从那个 frequency 的变化，我再拿出来它的模量。好，OK。这个时候我们就是用这个就不用这个了来 OK，我们要回到这个地方来，这个，然后呢回到这个OK，然后我们去 select probe，go to select probe，then select probe，this probe is 300 right？ RTSDA 300 right？
Yeah.
300 RTSDA 300。Okay. So if you choose the RTSPA 300, we give the deflection centimeter already, right? So that means we just use this value. We don't use the calibrate. So we see then the data is here or not. If they are not here, just give this data. Okay. Okay. Then come to the negative. So we will navigate. Then we focus on the surface. So, so before check the surface, if the surface is quite difficult to scan the surface, we use the tip reflection first. Almost near the surface, right? Okay, this one is the surface, but we use the tip reflection. So that means it still have the 2000 meter from the tip to surface. So we change back to the surface. And you can see here is your surface, right? Okay. So when you get this surface, check your parameter first. So the parameter, okay. So just now we use this one. For the so just now the Liu Yang checked to the QNM. That's why they changed to the lake shore. This lake shore include this temperature measurement. So you can change back here. Actually, this one is the same. 大概死掉了。Then go back to the mechanical system here. This one only not include this temperature control. Okay, and check the parameter from here. Okay, this one is 80, 60. And this one we just use this one is 42, right? And this one is if this is a new probe or the old. This is a new probe with the 10 nanometer. And check the parameter is 25. Okay, and let's engage on the surface first. Before engage on the surface, this probe is a little bit hard. That's why you can change this one to the smaller value. Okay. So this one maybe 0.02 is enough. Okay. This one is for the amplitude. For hard sample, 30 micro is okay. Okay. So also you should keep this engage amplitude is same with the peak force amplitude. Just engage on the surface. This is the setting. Okay, so first this is too small, so they are not engaged on the surface. Maybe this one is not visible high. Okay, so let's see the indentation depth. 哇，这有这么大的，这能压中你的药片。哪里来？分发药力。对，这indentation depth 的形式有这么大。indentation depth 有这么大吗？你
样品很软的。
啊？
它样品很软的。
它药品很硬。他说他药品很硬。
那硬的最硬的跟你不同。
你
那问题是很硬，就是我不知道这个膜是不是也是那种。
这
你要的
这好大呀，这一超过100纳米了。indentation depth 啊，这也忒硬了点啊。有点小啊，说明很软呀。
很软，就是
它已经压下去了100。
一插人真的去100。
对，因为这个镀的膜，它可能不是那个筷子的型号。
所以你这不能就不能用这个针了哈。
软一点的，
就用软一点的针呗啊，用软一点的针呗 ，OK。啊，所以这个不太正常 ，OK。
但是硬针它的软材料，它那个模样是不是？
你测有没有测的型吗？我让
你测的型，对呀，你的型号。
啊，对，型号可能。
等会儿先，你现在这个型号也不正常，啥也不正常，这个 OK。哎呦，这怎么会啊？这个力已经很小很小了。这个力已经很小了，而且这个地方怎么 variation 这么大？对，我先给你做表面图吧，先看看表面图里面。OK， 表面图的力已经不够了呀，已经不够了。先把表面做出来。这表面能重来做。
这种测的比较轻化，会不会是
模量？那肯定是不准啊。
也不准。
你是这个模型，我们昨天讲过了，我们适合的是赫兹模型。一下差了100多，它已经完全不适合赫兹模型了。哎，对，你的模型已经不正常了。哪一个？
是那个 model，
对，差的比较深。
不是要到赫兹模型了吗？要到那个 Sneddon 模型去吗？啊，那个 Sneddon 模型在这边我们没有去计算的，哎，这边没有去计算 Sneddon 模型的。你说啊，你不用选，这里面 Young's modulus 的计算只适合赫兹模型。它不适合 Sneddon 模型 ，OK， 在这里是不适合那个 Sneddon 模型。offline 可以。
现在我看了那个 Slender 的 channel 的机器人，那个人吗？
哪个？
这
个 Slender？
对。
应该是可以的，但是这个参数会改。
改定。
对，你不是这个地方应该是 angle 不是 r 了。
对。
所以你得有地儿输那个 angle， 不是这个 angle， 不是这个 angle， 有那个 angle 的，因为那个是那个针的这个 angle， 不是这里不是这个 angle， 这个叫 tip half angle。你如果是这里面像你们这个新的模型里面有这个的话，也可以选。可以选。你看你现在的这个针根本就它样品太粗糙，样品好糙。然后是把这个激光往里面调。 然后再做一点小振幅吧，振幅可能有点大，而且它这种镀膜，你们看到它这个为什么是这么不正常吗？它这个镀膜它镀的不知道这个地方到底是你镀了多厚这个膜。
好像是600几十纳米。
如果你的基底也是这么这么粗糙的话，你镀的有的地方可能根本就没有地方，可能就是基底。这镀膜你底下至少得很平啊才行啊。你们现在看它的这个东西，你们有没有发现什么问题？你看它这个，本来这个膜像它这个样品很平，对吧？那我应该哪个地方是不是都应该 focus 的非常清晰才对？但是你们看看，我挪到这儿的时候，这个地方不清楚，只有中间这一点点，它是有高度差的，所以应该是你这个样品并不平。不是你的样品本身应该凭这个就没有平，或者是咱们这么厚这个样品就有问题。这么大样片的时候，这么厚样品是有问题的，因为中间只有这么一个洞是有 vacuum 的，你的厚会厚成这样，会厚成这个样子啊。我再试试吧，看看你这个东西到底。不用，它这个地方呢，它是有其他的地方是有这个什么的。它其他地方是有 vacuum 的，你要开其他地方的 vacuum。还有刚才谁说我们收的时候能不能拿到这么一个区域的图？我们现在拿到的就是这一个区域的图，听到了吧？你不需要再去 export each point to the first tower，because already have the calculation value。So at this set, they have the first curve, force and time, and force and the say. So this first curve should be correct. 那你的这个 first curve 为啥这么差？你一直有这么再小一点啊？对，你这有人要来用机器了，10个吉他，5个微粒，好的这个样品。你的样品这么粗糙，这完全下不了针啊，怎么？这小的是为啥完全下不来针了？这样平板了，这是为啥我一直下不来针？我这么硬的探针下不来。我下不来针。会靠这样品吗？完全下不来针，它是吧？针根本就下不来。说是针有问题。 就会正常。哎，这边是正常的。哎，这边正常，也是不正常。OK。有，因为你看它这个一直在往下撑，看到没？这个一直在往下撑，一直往下撑。我的那个就是样品不平嘛，所以一直往下撑。哎，这个一定要是绿色的，下针它必须是绿色的啊，那个黄色的就已经有点不正常了。OK，现在基本上正常了一点了啊。哪个？我那个下针的力度加大了一点，然后它样品不平的过，就是因为样品不平，所以我一直往下沉，一直往下沉。对，但是我缩小一点范围是 OK 的啊。这个是这个力曲线已经 OK 了啊，力曲线已经 OK 了，我的 OK 看一下。现在这个把这个是30、60，然后再看，我这个现在一下。OK，所以它这个压入深度应该没有那么大。这么硬的样品，跟我说这么硬的样品，但是还是能够压动啊，还是能压动啊。你的薄膜没有那么软 ，OK，但是你的薄膜没有那么软，但这个这个 OK 了，哎，对，啊，这个没有那么软，OK，OK，但是某些点还是不好，你看它的某些点还是不好，看到没？所以它那个给出来的那个值是不正常的。然后呢，我把它这个offset 一下 ，offset，OK，从这上面看，你的大概就是，我能够测到的这个，大概是应该是在几个基帕是，它的有的地方能够压动的地方，我们基本上都能够压动了，所以它给它的 variation 太大了，就是有的甚至已经跑到多少 g 帕那个地方可能就不太准了，但是比较准的应该是这底下这个 ，OK。就是1-2个基帕的地方应该是准的。OK， 20，30，OK，应该在这个地方是准的。所以呢，就是这个针，这个针的有的地方，我知道它这个是底泡新的那个薄膜，薄膜上面可能有一些contamination，就是你镀膜的时候上面并不致密那个东西。
对，这个膜是不致密确实不太清楚。
所以它是不致密的，所以上面是有很软的东西的所以你会发现你的地方有很软的地方，那这种软的这个地方呢，我们的这个膜量是拿这个针是可以测的。OK， 就是对，有可能是你这样看的话，你的软的地方大概是在一个基帕左右，在1个基帕左右，甚至更小，甚至更小，对，甚至更小在1-2个基帕左右。然后呢，剩下的这种地方，这种看着这个压入深度比较浅，这个地方又比那个这个模量给出来几十个基帕的，这个真做不到的，所以是有很大很大的误差在里头因为我也没有校准这个探针了这个 tip radius 什么我也没有校准，它会有误差，但是你的这个软的地方是你的上面没有那么硬，你的样品并不硬 ，OK， 而且你的 variation 很大你表面不是粗糙度，是你的硬度上面这种颗粒和颗粒之间的 variation 也特别大。OK，你可以看出来，你这个颗粒有多大的这个反差，这个地方你看这种地方就是比较软的地方，这种地方就是很硬的地方，所以它的分布也是不同的有啥区别？而且你看，我们现在是扫了1个微米，如果我扫2个微米的话，你扫大的，像它这种地方，可能就 变化很大，坑里和这种地方变化很大。你这太不均匀了，从上面你这是粗糙，太过粗糙了。OK，
像他们这种说多少个 cycle 的是什么意思？
所以的 cycle， 它这个不是图做出来的，它这个是线做出来的，一个点的，这是一个点一个点的数据，这是图。
那你说这个图可以搞出来，然后再上面画点。
它这个cycle可就不是画点了，它是在同一点一直在做。
那这个呢？
那不是课我这昨天咱们做你的样品的时候，你忘了不是有个到那个 ramp 里面的 continue ramp 呀？然后你就一直踩呗，踩那一个点的，那是同一个点的是不是？这个不是。那个谁不是要看那个图吗？看到没？这不就图都出来了吗？
我要看那个均值在哪边掉
均值在哪里掉哈？这是这是咱们昨天做的那个我去找一下咱们昨天做的那个咱们昨天不是咱们昨天做那个图呢？怎么又死掉了？那个卡住了，回来了哈。OK， 然后我们去调我们昨天做的 KNM 的那个图，这是 Sapphire， 这是 nanoDMA， 这是nanoDMA Sapphire， 然后咱们昨天做的图，这是 Auto Capture 这个是 Pixelforce KNM 哈，对吧？这是 Pixelforce KNM。OK， 这是高度图对吧？然后呢，我这里面就是有我的模量图，对不对？这是模量图，你这个模量图，你去分析的时候，如果是一条线上的模量图，你可以分析这一条线上的这个模量，每一个点的模量出来了，对吧？要想做平均的话是这个，这是平均。roughness analysis 的 image roaming 就是这个，哪个？image roaming 是指的，就是因为咱们有的地方是拐了弯的，就是里面有 override，所以呢，你的 image 是包括了这个 override 的。这个 image 里这个 override 这个角落的这个地方的 point 也算。它俩在你看它俩是差不多的，很接近，所以一个 surface area 和咱们看到的那个 area 是有区别的，对吧？咱们不是5乘多少嘛，对不对？如果是5乘5的话，应该是25嘛，对吧？哈，咱们算出来是25，但是这个 image surface 不是25。这是只是后面旁边我这个减分过去的时候，就有一个这样子你又看这只就好了。如果看 adhesion 的话，就调 adhesion 通道嘛，那个 adhesion 通道嘛，这是 adhesion。如果你要看平均那个什么的话，就到这里面去看平均的 adhesion， 不需要一个点一个点去弄，不需要。人家已经给你算出来了，你再自己去算，对吧？你再把他的意思是说，我把每个点的力曲线弄出来，我再用那个 2box 再去处理每一个力曲线，那你不是费了劲了吗？人家都给你算完了，你干嘛呀？
如果自动校正的话，
你不是说，如果我现在这样 capture， 我就这么 capture 出来的这个图叫 FTM 点 FTM， 它只有图，没有这个力曲线，你没有返回的过程。我的 modulus 它给了你多少就是多少但是你不是讲返回吗？对不对？我重新去校正我都看见，那个时候是叫做 PFC 法。咱们昨天收了一个 PFC 是吧？在哪个来着？在上面好像不对，
在这里，这也没有那个。
就这里，咱们的 PFC 呢？再往下 ，OK，PFC 这儿，这不是咱们只有这个 PFC 是你可以做完了以后，你再重新去校准你的探针。你觉得你探针校错了，你重新校完了以后，到这里面是可以改的，改完了以后，这个模量是会 不对，你这个东西为啥每次不对？
正常不对，
不会的，
打开都这样的。
每次打开是这样的。OK，就是你的 background 扣的不好啊，给你扣一下 background 啊。这个时候是每一个点有立曲线的。做完了没有？还没完。哦，好，那是不是这个立曲线？这个时候的这个模量，你看现在，假如说我现在读的这一点的这个模量给了你是70，对吧？假如说我现在重新校准了我的这个探针的这个直径是20，然后呢，我 recalculate， 你再看看这一点的这个模量是多少？看到没？来了吧？所以你重新校准了这个模量。而且这个时候的图是你给出来的这套参数的，是不是可以给了你返回的机会？在这里你可以选 slide 模型，如果你的压入深度很大的时候，可以在这里选。在这里可以选的。好，是不是图就出来了吗？你看这个还有什么问题吗？它这个它的样品不行，它样品太这么稀不行。而且你的样品根本不是那么硬的样品。你这个可能上150就可以。这个探针有点硬。你的上150就可以。它的就上150就可以了。还有什么问题吗？
还是想让你就是讲一下，就是那个 continuous
哦，这个就是你看，我现在下到这个样品表面。这个 engage 到这个样品表面上去以后啊，OK， 然后呢，你不是要 ramp 一个立曲线嘛，对吧 ？ramp 一个立曲线，如果是在这同一点一直在这样 ramp 的时候，是不是做单边形图都是干这个的？就是一直光做曲线不做图是一个点的。我就是你看，我现在下针下到这个，我并不去找图，我直接到这个 ramp 里头来。然后呢，这个探针是在现在咱们这个下针的位置的正中间。然后呢，你看它这个下针力度，这够深。这地方不知道就下到这个偏的地方。
得确定一个不漏的这个理据。
哪一个？我已经设了，我刚才不是有设吗？OK。你看它这样品一直在飘，看到吗？一会儿上一会儿下，一会儿上一会儿下。
就是您说，如果要是这个是绿色的，那就是正常。
那就下来了。它现在这个就没有下来嘛？你没看到没下来吗？你这个就完全没下。太大了 ，OK， 太大了这个。这个样品不行，我给你换一个样品给你看吧。你不拿你的样品，你的样品更加难做。你的样品更加的小，它样品不平。我拿那个golden这个样品来。那是力最大的力点，那个不是没有不是漏的，这个里头跟你说的那 nanoDMA 是不一样的。你看到那个图是 nanoDMA 的图。
你说我刚才给你。
你的是 nanoDMA 的图。
这个不是那个 force。
是 force， 但是它不是拿这台仪器做的，它是拿 nanoDMA 做的。
纳米压痕。
老
师，你怎么一下子看出来就是
你看他给着load unload 那个过程的那个都是纳米压痕的图，这不是这里的图。哥哥，你那边还有什么其他的样品吗？
这个展艺娱乐那个人去拿样品。他是只想测那个水银胶那种。
那个对不起，做不了，他那个做不了。
对。
不用想，他都做不了。
还有另外一个问题，
这也不是，你这个里面的图全部都是拿到 indentar 上的图。你给我一个随便一个样品。你还有没有其他的标准样品？
标准样品
就是这个哈。
对。
他一个给我一个小一点的样品就行。
想看什么？
没有，他要看那个 ramp first curve。不是，我现在你这个里面的这个又
就几个了，
就剩这几个了。好 ，OK， 好。你因为你这个东西太那个什么了，太硬了震啊，对，所以我也，你这个不是 AFM 的图，这个 first curve indentar 的和这个都是一样的，它是 load 的图，你先去看看，你一定要看清楚它用的是哪一个，听到没有啊？AFM 的 load 的那个curve first curve 是这样子的，是对的。但是它那个计算的方法，那个前面那个图不是的。OK， 哦，哇，啥东西再想一下，吓我一跳。OK， 好，它这水泥胶的，你叫它不用拿过来，对，拿过来也做不了。都是水，咱做不了那玩意儿。咱也没有液体碳电钾。OK， 这是样品表面，你看啊，你不是要 continue ramp 嘛？然后你这个 parameter 的时候，把这个都放成0，记着啊，这是 AFM 在做 first curve， 然后做完 first curve 以后，然后呢是在一点上，它才去再去做它的分析。你刚才看到的这个是人家分析出来的每一点的结果。我昨天给你做了呀，你忘了？你不是收了一大堆的力气吗？就是那个一个点每一个点，你把它抻出来的数据，画成了这个图。你看到的那个东西应该是单分子力谱的结果，就是他做了成千上万个力曲线，找出来几千1000个好的，他去做分析出来的，然后他再做一个统计。OK， 你这个东西呢，你忘了咱们昨天做力曲线的时候，我下针下到样品表面了，你看啊，这是已经到样品表面了，对不对？这不是一个力曲线吗？对吧？这是这一点的是吧？哈，这是这一点的力曲线。哇，这个真好印！你们看这个哈，这个就是下针力度太大了，在中间戳了个洞。我这中间给戳了一个洞，天呐。啊？针不会断了。针不会断了，但是针会粗了。这个针会粗了。这个是哪个值大了？这个值大了。这个值大了。把这个值放小。下针的时候要放小。OK， 好，现在不是要看一个点的力曲线吗？对不对哈？等会儿啊，先看一个点的力曲线，你看到这个 ramp 里头来，这是一个力曲线。这个参数要改，因为刚才你们好像弄了好大的这个引导，这个应该是0.300就可以了。然后呢，这是力度，这个推歌吹手25好像没有压到。再来一遍。还是没有压到。没有压到的话，我就 continue approach。Already on the surface， 那就太大了，力太大了。然后这个是
两个参数是什么概念？就是是不矛盾。
这个 trigger 就是你最大的力点啊，最大的力点。这个 safety 是，这好像没有压不到表面，压不到表面了吗？怎么压不到表面？在表面，在表面，现在的力度就还可以，25有点太大了。
你不接也可以，对了，那我后来。
200米，然后怎么不动啊？这个没有啊，为啥不出图了呢？还得单子，这边是挨着300纳米，500纳米。让它阅图了。冲到表面去了是吧？出来了，冲到表面，这几个。哦，OK，好，看的是那个太大了，这针已经，这个针已经完蛋了，对，这个针已经戳坏了，所以它这个走不出来了。
老师，就是这个地方如果是模糊的，它是对结果有影响的。
哪一个？
这个。
那个可视化那个跟那个没有影响，影响不大，那个影响不大。然后是说，好远回不来，对，压不进去。它压紧，你看它没有抬起来，这边没有抬起来，你看这个没有回到表面啊，是没有回到表面啊，很黏啊。这个样品，这个探针好像已经不行了，它没有回来啊，没有回来。我实际上要让它回来，然后呢，它现在是没有回来。1500，再看看能回来了吗？这针已经不行了，它回不来嘛，你看回不来。它回来了哈，还是没有彻底回来，斯堪这没有抬起来。OK，好，你看就是这不是一个力曲线嘛，对吧？你不知道这针怎么了哈，这个针抬不起来，不知道为啥，再加大一点力，然后那个这已经很大的振幅了。我换一个方式看一下啊，PM 里面这个方式不行，换一个。在这里面看出看会不会好一点。我知道为什么了。OK，那个戈登装的这个针没有 A。 做 QM 一定要用那个有 A 的探针哦。有 A 代表反光性好，因为它这边只有1.2，看到没？要用度里，
那个我们是跟机器一起的，
有一盒是没有的。OK，
应该是 underwater。
那这不是立体线
那种可能是在空气里面测的。
对，这是在空气里面测的。
就是用那个做水银胶，特别可以做，这就
也因为它如果不进水，是它水凝胶是很多水，不进水，而且你的不是长时间泡水里是可以的。你这个的 probe 的 back end coating is good or the aluminum. If it's good, no problem, you can do. Even the coat is aluminum, not longer time to shake inside the water, still can be used. Okay, so it's a short term, not matter, maybe 1 hour. Then the aluminum layer is still on the back side of the silicon. It's okay. OK，so 这个不是立体线就出来，你那个怎么拿到的？就这样 ，continue ramp，continue ramp，continue capture。OK， so if you continue capture, you can get a lot of the first curves, right? OK, please stop moving capture before changing. OK， 就是你一直 run， 一直 capture。那你就能够拿到好多个图，对吧？哈，有 continue 哈，有 continue ramp， 然后有 continue capture， 然后咱们现在在哪？
就是每次都得自己再点一下那个，就是这个。
对，你得 capture， 你不 capture 你就没有图啊，所以你 capture 的所有的图就都会一个给你出来，等你。later 你是一个一个拿出来去分析的。
老师，你的意思是说我这个 continuous 这个 tap 的时候已经是 tap 了，但是我每次我都得点。
那要不然他这边不会跟你换呀？你不点这个你怎么 capture 到图啊？
那我得点1000多次啊。
你不要点呀，点完了然后他自己给你换啊。
然后他不想要了我就再摁一下。
你不要了你就 stop 呗。你要报这是连续 capture 啊。然后呢，你这个你就不做了，就 stop 了就 OK 了。哎，这个你是自己 automatically increase 的 number， 因为你不用一直给他说，不用就这样你看你现在咱们都收了50、60个嘛，那一会儿对吧？这样子这会明白了哈。你看这个针不适合那个 QM， 咱们在 QM 里面一直下不了，对吧？所以呢，你看你这个就。OK， 这很明显。然后位置照，
我们可以用适合 QM 的针，然后做这个。
可以，一样的，明白了哈。行，那个高登剩下的就交给你整理吧your sample is too soft for this kind of probes, and also then
You want to try different
this one. Yeah, but today I'm not time for travel you.
Yeah.
Okay.
So
you can try this one. You can try this one. But you only can try the first one. Maybe you cannot scan on the thing. Because this one is quite bigger, right? It's quite bigger. It's only for the less kind of the first curve. You can just engage on the surface. Just run. Okay, like that.
Okay. Yeah.
Show first curve. Just the first curve. Okay. no problem. When you engage on the surface, you can check these parameters. So you go to the check parameters. If this number is very small value, then you just engage on the surface, go to the ramp, then check the ramp for change the ramp size, ramp rim, then you get the one for the. If you cannot, at here have the continue ramp. This one you continue ramp when you continue capture. Here sometimes you just. 没事，啊，你不用动啊，你不用动。对。
哦，多两个你。
别。
我去开车，我到你。
走了啊 ，OK， 来。So you can make WeChat. Now yeah, you can add one WeChat.